Welcome to the last session on the first order methods in optimization. After this talk we will have a lunch break, and then there will be one more talk, like the last talk of the interdepartmental method sessions, right after lunch. So the speaker is Reza Eghbali from University of Washington, and he will talk about interesting connections between first order methods and online optimization.
All right, thank you very much. I'm pretty lucky because this is the last talk in the continuous method, and so you've seen a lot of the stuff that I may be using here in Lorenzo's talk, Stefanie's talk, also some Russian's talk. So you all know what optimization is. You have a problem, it's got some data and it's got some variable.
Excuse me,
yes.
is your microphone on? I haven't heard it.
So the person in charge of microphone
Is it switched on? Like, can
Actually switched on.
all right, switched on. So, okay, that's better. And you've got some data and some variables, and you probably go and apply some iterative method to solve your optimization problem. And let's call that offline optimization, when you got all the data beforehand. In the online setting, things may be different. So in the online optimization setting I consider here, you have this notion of time. At each time step t, a new variable comes to you, and the data associated with that variable also is revealed to you. The online algorithm has to assign a value to that variable, and the catch is that at time t plus 1, when new data is revealed to you, you cannot go back and change the assignment you previously made. And you have to make the assignment without knowing what's coming in the future, because by the definition, future happens in the future. So the metric that is used in the literature for gauging how good an online algorithm is performing is one of them is competitive ratio. Now I'm using metric in a colloquial form, not in a mathematical metric sense. And that is defined as the ratio of the objective achieved by your online algorithm to the offline optimum. So in order to set the notation and have some general problem we can work with, let's consider this problem first in the offline form. You're trying to maximize a function psi. Your variables are these xt's, and these xt's can be vectors. And you have these local constraints on them that requires an xt to be in some set ft. So the constraints are local, but these variables are coupled together because your objective is psi applied to the sum of xt's. And let's make this assumption that psi is a concave function, and to make things beautiful and nice, that maps a cone k to the real numbers. And the cones that are really of interest are the positive semi-definite cone and the non-negative ortho. And FTs, let's assume that they are convex compact sets. So the entire problem is a convex problem. You're maximizing a concave function subject to constraints that are convex. In the online setting, the online algorithm knows what psi is beforehand. So that's an information that it has. And then at time t, there is an adversary that gives the algorithm ft. And now the algorithm has to assign a value to xt, choose xt in ft, basically. And once that assignment was made, at time t plus 1, same thing happens with ft plus 1 and xt plus 1. And this contains quite a few online problems that people consider in literature. It may not contain some other, even classical ones. Quite a few problems that people considered can be written in this format. At least they're convex relaxation. Many of them actually on positive ortho. Any question on the basic setup? So here's an example of such a problem. That's the AdWords problem introduced by Mehta in 2007, and it's a generalization of online bipartite matching. So suppose you are a search engine, all right, so like Google, and there are a couple of advertisers. The number of them is fixed, and so people search something, so they enter some query. When a query comes based on what are the keywords in that query, some of the advertisers bid on it because they want their ad to be shown to this user. And you know, Google has paid a couple of $100 million to AdBlock, so AdBlock doesn't block the ads of Google anymore. So this is really of practical importance. So if you want to map it to the notation of the previous slide, when a query comes and advertisers bid on it, it's like the set that is given by adversary has the bids on it. So this is the bid of advertiser 1 on query 1, and this is just the first standard basis vector, standard vector vector in the standard basis of Rn, and this is the bid of advertiser 2 on query 1. Sorry, that should be advertiser 4 on query 1, and this is just a vector that is all 0 with the exception of the fourth entry, which is 1, and so forth. And so you may also put a 0 vector here to give the algorithm the liberty to not even show, to choose 0, meaning that you don't pick any ad here. So the online algorithm picks one of the ads, which is equivalent of setting x1 equal to this w1e1. And this game or this procedure continues, and it's an online procedure. Once you make a decision, you cannot go back and change it. So what's the objective? Whose objective? Advertiser's objective? No. The customer objective, the people who are searching? No, that's not the objective. The objective is search engine. Search engine wants to maximize its revenue. And so when these guys bid on it, and if the bid on a query, and if the ad is shown, they pay equal to that bid to the search engine. But the catch is that the advertisers have a limited budget. Say they have a daily limited budget. So, and the search engine knows that. All right, that's then the utility or the revenue of the search engine for each advertiser, it's got this function psi I, which goes up linearly up to the budget of advertiser I, and then flattens, meaning that at this point, assigning any, picking any ad by that advertiser is not going to end up generating revenue by the for the search engine. So your entire utility is this function. Let's call the entire thing just capital psi applied to the sum of these x's which have the bids on them. Closely, another place you've heard the word online is online learning. Also, some people call this online optimization, but I'm not going to do that in this talk. And people who were present in Sasha's talk, they were introduced to the concept of online learning if they were not before. And in that setting, what happens is that the algorithm chooses, the online algorithm chooses a vector by t in some set D. And then once that vector was chosen, the adversary reveals a loss function. And the algorithm incurs the loss of LT by T. The metric in that setting is something called regret, the way you gauge the performance of an algorithm. And that's the loss accumulated by the algorithm during the m step of this sequential process minus the loss of the best decision. So that's the one fixed best decision you could have made, and put that minimizes the sum of the loss, all the losses. And one algorithm that can be used, for example, in this setting is follow the regularized leader algorithm, which is similar to dual averaging of Nesterov. It picks yt plus 1. So it's say you have progress up to time t. Now you have to pick yt plus 1 in the, as the minimizer of this inner product, which is the inner product of y with all the gradient of your previous losses plus a regularizer. All right? And so here you have to go find a regularizer that gives you a good regret. For example, people find a proper regularizer that is strongly convex enough to get a 1 over, to get a square root m regret. So, all right, sounds similar to the previous problem that I mentioned, but it's also different. What is the connection, and how do these things relate? So I try to go over these things during this talk and a little bit further. But before I go any further, I want to point to the fact that, first of all, online algorithms is a big part in CS theory, and there's plenty of work done in it. If you are like me, if you are from continuous optimization like me, you probably will enjoy reading those results in the literature where they introduce and they analyze their online algorithm as a primal dual algorithm. And very fundamental work has been done on these online primal dual algorithms for various online problems by Sefi, Niv Bookbinder, Kamal Jain, by Nikhil Levanor, by Yossi Azar, and many other people. And I'll, if one wants to start learning about online algorithms, I guess these are very good places to start reading. On relationship of this type of, on relationship to regret, in the last few years, a couple of work has been done on different settings. The worst case analysis or random permutation analysis. Interesting work by Devanor. We did something in the around the same time on random permutation, and then after that on the worst case analysis. So in this remaining 45 minutes, I only get to do very a small introduction, basically, to this area. And and this is what I'm going to do. We're going to try to go over the worst case analysis, competitive ratio analysis of a greedy algorithm applied to that online problem I first introduced. And through that analysis, we see the connection, through the introduction of the algorithm and the analysis, we see the connection to the regret setting. And then at the end, depending on time, we go over this idea of a smoothing or designing regularization to move further from greedy algorithm and get better competitive ratio bounds. Of course, in online optimization, greedy is usually just the performance of greedy is the baseline. You have to beat it. You have to give better algorithms. But to understand connections to regret setting, it's good to go over the analysis of the greedy first. Any question? So I mentioned primal dual, and we want to look at primal dual analysis. The connection with regret is becomes obvious when we write the dual. So let's just see what's the dual of the original problem we wrote. And just in case you forgot the original problem was we wanted to maximize this subject to xt being in f, right? And psi was concave. So the primal problem was a maximization, the dual is going to be a minimization, of course. And it has two parts. The first part is the conjugate of psi. So if you were in Lorenzo's talk, you saw the definition of conjugate. Here my psi was concave when I started. So this is the definition of concave conjugate. It's so concave conjugate at some point y. Let me just explain over the picture. You have your function psi, it's the blue curve, and then you have just draw a linear function here, which is the inner product of y with u. U is your variable, y is the slope. And look at where the distance between these two in terms of function value is maximized. So that distance is going to be, or that difference in function value is going to be the negative of your conjugate. And then you have, for each one of these individual constraints on x over here on the board, you have a support function dual, which is defined as the value of support function is achieved is the maximum of a linear function over the set ft. And people who are more familiar with the concept of conjugate, they know that this is basically the conjugate function for the indicator function of set ft. But if you're not familiar with it, it's okay. Just to finish. Now, we want to look at greedy algorithm. Of course, greedy algorithm is very intuitive, but it's good to, I always like to get to an algorithm from the optimality condition. Because after all, whatever algorithm you have, you want to compare the objective of that algorithm to the optimal solution. So let's see what the optimal solution is in the first place, and see what the algorithm should do to be able to get something close to optimal. So here's the dual again, just for convenience. The optimality condition, the primal dual optimality condition is this. So a pair of primal and dual variables, so x is our primal, y is our dual variable, are optimal, or this is an optimal primal dual pair if and only if your y is the slope of your function, is the gradient of function at the sum of the optimal primal. And then the x's, the optimal x's, are the maximizers of these linear functionals over ft, where the linear functional is defined by the dual variable, y star. And so here's the optimality condition up there again. And let's look at greedy algorithm. So what does the greedy algorithm do? At time t, you give the greedy algorithm ft, and it should assign a value to xt. In order to distinguish between the generic variable names and the one assigned by the algorithm, I just use hat for this greedy algorithm. Right? So what the greedy algorithm does, it assigns the primal xt as the maximizer of a linear functional, but the greedy algorithm doesn't have access to the optimal dual variable, so it just keeps an estimate of the dual variable. And the way it updates the dual variable is by, once the primal assignment was made, the dual variable is updated by setting it as a gradient of psi, evaluates it at the current sum of your points. So if you just compare that to the optimality condition, you see that it's very similar. The only big difference is that you don't know what's going to be assigned in the future. So you have only the sum from 1 to t rather than sum from 1 to m. And here you have some estimate of dual variable, not the actual optimum. And again, another viewpoint of the greedy algorithm would be something like this. So this is more formal version I've written here. I call it sequential greedy algorithm for reasons that become clear in a second. it has an estimate of dual variable at time 1, sets that estimate to be the gradient of psi at 0. All right? And then, so basically, if this is your psi function, you look at the slope of psi at 0. And then once the f1 comes, it says x1 as the maximizer of this linear upper bound on your function over the ft. And once that assignment, and makes an assignment x1. Once the assignment was made, it goes and again finds the linear upper bound over the concave function, which is given by the slope of function at this point, and then assigns x2 as the maximizer of that linear upper bound, and so forth. So this is basically Frank-Wolf algorithm, but a coordinate version of Frank-Wolf algorithm, where you, to each coordinate, you apply only one step of Frank-Wolf algorithm. Now, from the dual point of view, you could have also, so this is the same thing on the board. The difference is that here I plotted the derivative of psi, and the assignments are being made, and the y's and x's are being updated. But you can also, you can also look in the dual update is always this. You put once you make your primal assignment, you put y as yt plus 1 to be the gradient of psi at the current sum. There shouldn't be no a here. There's no a. And but you can also rewrite it in a way that makes the connection to the regret setting. You can write your dual update as choosing your y hat of t plus 1 as the minimizer of this individual and this comes by the properties of the conjugate function. And now if you look at it, this is basically follow the regularized leader with this specific regularization minus the conjugate function. And these guys are basically the gradients of these support functions. So you remember we defined the support function to be, I could have just put max here. So and this, because of the fact that xt is actually the maximizer of this by the definition of the algorithm, xt becomes actually this. Now this is not really gradient, it's a subgradient, but I don't want to go into the definition of subgradient. So if you want to map it to that regret setting, basically your loss that I said adversary gives you a loss is just that support function for ft. All right. Any question? So now you may ask, why do you want to just why do you want to maximize the linear upper bound on your function in a coordinate fashion when you can just maximize the function coordinate wise? So let's that gives you some other version of greedy algorithm. Let's call that the simultaneous greedy algorithm. The reason I call it simultaneous because if you write it in the primal dual format, it's equivalence of updating the primal and dual simultaneously together by solving a min-max problem rather than updating them sequentially. So this is basically a coordinate maximization problem, one by one. When a new ft comes, you put corresponding xt, as the maximizer of this guy. These are the things you already assign, and this is the new thing you want to assign. And for this algorithm, I use tilde, just in order to distinguish between the variables assigned by the algorithm and the generic optimization variables that we have. And in terms of this picture kind of summarizes what's going on here. You make an assignment to x and y kind of simultaneously here, and y, and this plot is the gradient of psi, or the derivative of psi. So y is following the derivative of psi at the current point. So now this connects to something that Lorenzo mentioned, which is the forward Euler and the backward Euler method. So if you remember, Lorenzo in his talk mentioned that if you want to discretize that continuous optimization that he had, you can do a forward Euler or a backward Euler, where so maybe if you're at this point u, you want to find an update to get to u prime, you can move. So for his minimization problem, you can move in the negative direction of the gradient at u. So that was equivalent to the forward Euler discretization of his continuous differential equation. But you can also do a backward Euler. Well, you can't really do it, but theoretically, you can set your u prime to be a point that satisfies this. So u minus gradient of f at u prime, not u anymore. So he called this implicit because this your gradient is evaluated at a point that you want to end up at. So there are similar things going on here, and that is the updates that are being done in this primal dual update. You can rewrite that thing as having xt tilde in argmax of x in ft of this linear function and yt tilde is in argmin of y of this guy. So x and y satisfy this condition if and only if they satisfy this. So you see xt tilde depends on yt tilde, and yt tilde depends on xt tilde, and you can rewrite this last one as yt tilde is the gradient of psi at so gradient of psi, that's from 1 to t, so includes t itself. This is in contrast to the previous algorithm where yt plus 1 was gradient of psi at sum from 1 to t. So this doesn't have the t plus 1 in it. And when you assign xt, you use the gradient that was calculated previous step. Any question? now let's look at the analysis. The analysis also give us more intuition onto connections to the regret setting. So we wrote the greedy algorithm in a primal dual framework. So let's use the primal dual value to actually try to find the competitive ratio for the greedy algorithm. The primal value achieved by the say the simultaneous greedy algorithm, the second one I mentioned, the primal value is psi applied to the sum of the x's assigned by that algorithm. And let's define the dual value this way. I put in each one of those, so the optimal dual variable is just one dual vector, all right? But our algorithm produced m of them, actually m plus one of them. So in each one of those support functions, I'm going to put one of the in one of those yt's. So in sigma t, I'm going to put yt, but inside the conjugate, I'm going to put the last dual variable. And so in order to get to competitive ratio, you can first start from just bounding the duality gap. So remember, that was a maximization problem that we were trying to solve at the beginning. So we want to lower bound the duality gap. And so look at the difference between the primal value achieved minus the dual value. So and by p sec, d sec, I mean the primal value achieved by the sequential greedy algorithm, the Frank-Wolf one, minus the dual achieved by the same algorithm, defined the same way. So, the duality gap for the first one is going to be just the conjugate applied to the last dual variable plus psi of 0. Let's just assume psi of 0 is 0, so we don't have a problem here. And for the sequential algorithm, you have similar thing with extra garbage. Oh, it's AT is also a type, but there's no AT here. The extra garbage actually has to do with the fact that you were doing this or your dual variable was lagging by 1 all the time. And so you pay a price. So I'll go over the proof of this really quick. The proof is very intuitive. Let's see if I can pull this off and you can understand it. So in order to, so I want to prove this duality gap bounds. So the first one, the simultaneous algorithm. So you can first look at how much increment or how much improvement in your objective you make at one step. So at time t, by assigning xt, how much I improved my function. So that's let's call this delta pc. That's going to be psi at this point minus psi at the other point. Now by concavity of psi, this is going to be greater than or equal to the gradient at this point times the difference between these 2 points. So then this is just the psi. This is sum from 1 to t minus 1. This is sum from 1 to t. So the distance between these two is exactly your xt. You added this xt here. So this is greater than or equal to so the left-hand side, or the one in the up, is at delta p seam. The one down below is an inner product. And you got that by concavity. You don't really exactly need concavity. You only need concavity in positive directions if you assume that the points in the ft are all of them are in the cone. So you only need concavity in the direction of cone. Because if the ft is always a subset of cone, which actually this was an assumption I forgot to mention. All the ft's are subsets of cone. So say the positive ortho, you're always adding to your running sum of xt's. And this is because of the fact that the primal variable was assigned through maximizing this, was taking the argmax actually. This is actually equal to the support function, sigma t, which is the soup of this over ft. And so it's now easy to get this. You just take the sum from t1 to m. These guys are going to telescope, and it's going to give you p sim minus psi of 0. And then you get this sum of sigma t's on the right-hand side and a little bit of manipulation. You get this gap. For the second algorithm, for the sequential algorithm, actually that was the first algorithm, that was that Frank-Wolf one that I mentioned, or the forward Euler one. The issue is that the issue is that your yt was lagging, all right? So yt was a gradient calculated at some at this point, not at this point. So what happens is that, and then the gradient at this point, if you, for a concave function, you cannot lower bound that function difference by xt inner product with yt, because in that case, that's going to be your this slope is your yt, and this is an upper bound on the function difference. So what you need to do, you need to look at yt plus 1. That's the yt plus 1 is a gradient at this point, and that gives you the same. All right, and but the problem was that the algorithm wasn't actually taking the argmax of the linear functional with yt plus 1, and it was taking the argmax with yt. So if you want to relate it to the support function, you have to add and subtract the yt to get the support function and some extra garbage. So this is a very simple calculus concept, is that, so if you think of it, the psi at sum from 1 to t minus some psi at sum from 1 to t minus 1, if say this is the red curve here is the gradient or the derivative of your function, is just the area under this curve from here to here, and you're basically estimating an integral. In the sequential algorithm, you're picking these y's, these slopes, so you're calculating an integral using a Riemannian sum. Well, when you do Riemannian sum, you can have an upper bound or a lower bound on the integral. In the first algorithm, you really have an upper bound. You're taking slopes at these points, all right? But in your proof, what you really need is a lower bound. So in order to get that, you have these extra errors here that are exactly these inner products, all right? While the simultaneous algorithm is actually getting a lower bound estimate on the derivative of the function, on the integral of the derivative of the function, which is the function. Any question? So I got a feeling that most people are lost at this point, so let's just look at the theorem to get even more lost. So what I gave you was a duality gap, and I just wanted to mention that duality gap is really related to regret, in that for that sequential algorithm, as I mentioned, what you were doing in the dual was follow the regularized leader with a regularization equal to minus the conjugate of psi. So then that duality gap that I had was actually in the proof of regret is what you get before the actual regret. if you go a little bit further, if you assume psi is Lipschitz continuous, or equivalently the conjugate of psi is strongly convex with some parameter mu, your duality gap is going to be this quantity. And in regret, the freedom that people have is that the regularizers, they choose themselves. So the strong convexity parameter, they put it equal to a square root m, manipulate these things well, this is basically minus regret in parentheses. Manipulate these things to get a square root m regret. Here the difference is that regularizer is not that much of your choice. You can't just put your regularizer whatever strongly convex you want, because you're in the business of getting competitive ratio and not just some duality gap. And in that business, you can give results such this. In order to turn that duality gap into competitive ratio, you can. We need an assumption first, all right? And that's let's call it diminishing return assumption. Stefanie talked about diminishing return, and this is the same diminishing return over a vector space. It says that if your v is greater than or equal to the if there's a v that is greater than or equal to, there's a u that is greater than or equal to v with respect to your cone. Now take the cone to be non-negative ortho, and that's going to be u is element-wise greater than or equal to v. Then the gradient of psi at u is going to be less than or equal to gradient of psi at v element-wise. In more general terms, with respect to the dual cone. So this is basically a first-order way of writing diminishing return. The zero-order one is going to be very similar to this, but in the vector space. It's going to say if you add a d, as long as d is in your cone and u is in. Right? So here's one connection to submodularity. So if you have such an assumption, the primal value achieved by, say, the simultaneous algorithm is going to be the lower bounded by some multiplicative factor times the optimum, and the multiplicative factor defines on a quantity which defines on your function. It takes the value of the conjugate of function, evaluates at the gradient, divided by the function itself. So this shows up in a couple of papers. Actually, this quantity in many papers shows up, even if they're not doing greedy, they're doing more advanced algorithms. But this quantity, I've seen it on multiple papers in their competitive ratios, and it needs a little bit of intuition. The best I can do, I can show you a one-dimensional function. So remember, the quantity is basically, you look at the ratio of the conjugate, evaluate at the gradient divided by the function, look at the worst case of this guy. And this scales for a concave function. For a monotone concave function, it scales from -1 to 0. So the best I can do is just give a one-dimensional example. Let's say the blue curve is the your function psi. At some point u, the value of psi is going to be the psi of u0 at point u0. The value of conjugate evaluated at the derivative is just the y-intercept of the tangent to the function at that point with a negative sign. So you're looking at the ratio of these to that and taking the worst case of that ratio. But for the first algorithm, the sequential algorithm, you don't exactly get a competitive ratio. You get some additive stuff which has to do with that garbage, or the Riemannian sum error. Now you may ask, okay, you remember in this assumption we got this, we assume that we have this diminishing return. You may ask, where did you use that? So the proof of this algorithm is basically you use that duality gap that I show you in combination with these two facts, that come, I can't say only, but they come because of that diminishing return. That dual quantities I define are greater than or equal to the optimal dual, and this is something that you can use diminishing return to show that. Here's some just facts that for the monotone function, alpha psi is greater than or equal to -1, monotone concave function, and that results in a commutative ratio of 1/2 for greedy algorithm. For non-monotone function, things are kind of more complicated. Question. So this is all good, but I hope at least you get some intuition about connections to regret. But now let's just focus on commutative ratio a little bit. And first of all, we had that assumption, that diminishing return assumption. What are the functions that satisfy those? So Stefanie actually had some of those in her lecture slides. So on non-negative ortho, the diminishing return assumption, any separable concave function satisfies that. Any twice differentiable function whose Hessian is element-wise non-positive. Again, you saw that in Stefanie's lecture. But we went to the trouble of these cones because we may be interested in more than non-negative ortho. So if you're interested in positive definite cone, for example, log determinant satisfies the diminishing return assumption. Trace of u to the power of p for p from 0 to 1 satisfies the assumption. And so these are useful to people who are doing experiment design and linear experiment design. These objectives may show up. So now, okay, so the first part is done. The second part in the last 10 minutes is that. Let me just ask any question. So, either I'm doing a very good job or a very bad job, one of these two. So now let's look at how one can move away from greedy algorithm into some better algorithms with better commutative ratio. In order to see why you need to move away from greedy algorithm, let's look at this cartoonish example where you got this function, all right? This is your psi, and you're doing this online optimization on it. You're applying greedy algorithm. You assign some value to x, and the corresponding dual is going to be the slope of your function at that point, which is 1. And then for x2, the same thing. The corresponding dual is 1. The slope is still 1. And all of a sudden, when you assign x3, the slope is 0. All right? But the greedy algorithm was blind to this fact. Although it knew psi beforehand, it wasn't predicting that the function is plateauing. So your return is going down. Had it had some more prediction in it, it may have been a little bit more conservative at the beginning because it knew what's going to happen in the future. Intuitively, it would have been a little bit better to apply greedy algorithm to a function like this. Okay, your original problem doesn't change. Your objective is still the psi that plateaus, but you apply your greedy algorithm to the smooth version of it. Now this has more prediction built into it. The slope is 1 at the beginning, but it gradually comes down to 0. So when the greedy algorithm is making assignments, it's basically looking ahead in the future and to the fact that the function plateaus and your return becomes 0 at some point. So then you mathematically, you have to, if you want to modify the greedy algorithm, you can go back and use a smooth version of your original function in the greedy algorithm. All right? Your original problem remains the same. Your commutative ratio is defined with respect to that original problem, but you just apply the greedy algorithm to a smooth version of it. So mathematically, if you want to look at it, the dual and primal, the dual updates specifically in the sequential algorithm And the primal dual updates in the simultaneous algorithm are going to be updated in a way that is basically changing psi to psi s. Now, if your psi s satisfies the diminishing return assumption, you don't need the psi to satisfy it anymore. You get a competitive ratio that is, instead of 1 over 1 minus alpha psi, is 1 over 1 minus alpha psi psi s, which this looks like a little bit more complicated. Alpha psi by itself is kind of hard to absorb. This is a little bit even more complicated than that, but intuitively what this is doing is basically measuring two things. Of course, you can go and smooth your function to death. You can put 0. You can put psi s 0. That's a smooth function, I know. But because you're doing competitive ratio, your psi s should have something to do with your psi. And that's a fundamental difference between regret setting and this setting, is that you can't just go and put whatever, because this psi s is the regularizer, yeah? The conjugate is the regularizer. You can't just put whatever regularizer, strongly convex regularizer you want. It should be related to your original function psi. So, and this quantity is measuring both of them, how far you are from how smooth your psi s is and how far is it from your original function psi. So now the question is, what are some ideas for smoothing? How can I smooth my function? So I come from continuous optimization background, so I automatically look at what people do in continuous optimization. So this idea of, I call it Nesterov smoothing, but goes back to Bertsekos, Polyak, or even Moreau envelope, which says that, take your function, original function psi, take its conjugate, add some other function to it, some other concave function, and take the conjugate of the entire thing, and that's going to give you your psi s. So this is your choice. This is something you should choose. If you choose it to be 0, all right, conjugate of a concave function under mild assumptions is going to give you back psi. So for example, okay, there was that AdWords problem, if you remember, I used as a motivation. You can go and choose this phi star I use, to be a shifted entropy. So the shift and everything are calculated in a way that you get a good competitive ratio. To get and then apply your grid algorithm to the smooth function, smooth with this specific shifted entropy, to get a competitive ratio 1 minus 1 over E, which is the optimal thing you can get. All right. So within 1 hour, we got to a 2007. We rederived the 2007 result. How many more hours we need to get to the current state of art? But probably 5 minutes. The same type of shifted entropy can be used to actually, rewrite or redrive results for online LP, because at the end of the day, AdWords is a special case of online linear program, and a more general version of this will give you optimal competitive ratios for online packing LPs. And redrives the algorithm in Bookbinder and Naur from 2009. So the last 5 minutes I say a little bit more of a research stuff, and which is how do you come up with this? Well, I looked at this algorithm and reverse engineered it to say, oh, this equivalent to it is equivalent of applying greedy to a smooth version of it, and this is the regularizer you have to use. But the question, how do you come up with these things from scratch? So it's not that obvious. So it would be good if there's a mechanism to design a smoothing. So it's an automated mechanism that you can use to design a smoothing. And so we realized that, well, one thing you can do, you can go back to the competitive ratio bound that you had and actually say, I want to find psi s that maximizes this competitive ratio bound with the condition that psi s be a dr function because I need that in my proof. So that's going to maximize a commutative ratio bound for you, and that's a convex problem itself. The problem is that it's an infinite dimensional problem. You're looking for optimizing over a space of functions, and even if you discretize it, for some general case, it gives you exponentially many constraints in the dimension. But in some special cases, it's tractable and you can solve it. One is when you have a separable function. So if you have a separable function on the non-negative ortho, meaning that you can write it as a sum of psi i's applied to the coordinates of u, you can write psi. Designing psi, designing psi s in the sense of going and optimizing your commutative ratio bound is an easier problem, and something like this. Still, this is an infinite dimensional problem, but you can go and discretize it, and you can go solve it, give it to CVX to solve it for you. And it basically reduces to designing the smooth function for a scalar function, using the fact that your original function was a separable function. Using this, you can, for example, recover some algorithms or results from Devanor and Jain on AdWords with concave returns, which is a more general version of the AdWords problem where the return is a more complicated function. Here's an example of that I have here for you. So my original function is plotted in red. So you remember AdWords was very simple. The function was a piecewise linear function with a slope of 1, then it plateaued. So let's just add one more piece to that piecewise linear function. So it has now 3 pieces. And I went and solved the optimization problem we had for optimizing the commutative ratio bound, and I got this smooth function. And then here I plotted the difference between the conjugate of the smooth function and the original function. And it's something like this. So look at this and you realize that this is not a concave function. So you could not have derived this smooth function by doing what I called here the Nestrov smoothing, which was adding another concave function to your conjugate and then taking the conjugate. You could not have derived that, this psi s, in that way. I have plenty of more examples, but maybe just
questions.
So for the linear AdWords problem, which algorithm do you eventually get using this method? Is it multiplicative updates?
yeah.
Other questions?
So when you're automatically kind of generating these smoothings, is that it mostly allows you, I guess, to get the value for the competitive ratio, but then the algorithm actually probably needs the exact function somehow, or?
So when we design it, what we get is the smooth function that the algorithm needs, and it also gives us the optimal commutative ratio bound that we had. So our commutative ratio bound was 1 over 1 minus alpha, the commutative ratio bound in that theorem. So maximizing that is equal to minimizing the 1 minus, is equivalent to minimizing 1 minus alpha, so it gives you that bound as well.
More questions? Let's thank Reza again. We have a last lunch break now till 1:30.